Thanks, Victor, and thanks for the organizers for putting this workshop together. Glad to finally be here. So indeed, today I'll be talking about anomalous Floquet topological insulators, but specifically I'll be talking about how can we get quantized response functions when we probe this type of systems. So I'd like to first, before going into the kind of non-equilibrium physics, just remind us about quantized response functions in the quantum Hall effect. So one way to get the quantized response function in the in the quantum Hall effect is just to look at the conductance, say two-terminal conductance, and say in the simplest integer quantum Hall effect, the two-terminal conductance would be basically equal to the quantized Hall conductance in the system. So this, I'll call this type of probe an edge probe because in this two-terminal setting, it really probes the edge states and transports particles through the edge states. We can consider a different probe, which I'll call a bulk probe for discussion's sake. This probe was suggested by Streda. Is basically by looking at the magnetization of the system and basically taking its derivative with respect to the Fermi level. And in that case, we also expect this derivative to be basically equal to the quantized Hall conductance. Of course, you can imagine that there is a close connection between these two types of probes. And in this talk, I'll basically describe the analog of these two probes for these time-dependent systems, for these anomalous two-dimensional topological phases. And I'll describe basically how to get a quantized response function for each type of probe, an edge probe or a bulk probe. So this is the outline. So I'll also make a quick introduction to Floquet physics. And then I'll be talking about, specifically, I'll introduce this phase, this anomalous Floquet-Anderson insulator. And then I'll be talking about these two probes, the kind of a quantized two-terminal current that we can get in the system, and the quantized magnetization. So just to remind everybody, so we're on the same page, if we discuss time-periodic Hamiltonians, we could use Floquet theorem, which basically tells us to decompose the evolution operator into a unitary matrix which is periodic times an exponential of a fixed matrix. And the eigenvalues of this fixed matrix are called quasi-energies. And one thing to note is that these quasi-energies, since this composition, I could always move omegas, frequencies of omega between these two parts. The quasi-energies are really only defined as an interval of 0 to omega. Now, if we're in a lattice, then we have, as we saw before, Floquet Bloch bands, which are labeled by the quasi-momentum and quasi-energy. So there's been a lot of discussion in the literature about methods to basically induce topological phenomena in, say, a system which, absent the drive, is not topological, or, for example, by subjecting, say, graphene to circularly polarized light, or using above bandgap radiation. And there's several experiments in the all-optical regime and in cold atoms, as well as in solid state. I'm not going to go into details. But now, when we think about probing the topological phenomena in these type of systems, we need to ask the question: can we actually observe these type of quantized response functions? Quantized, maybe differential conductance or a quantized magnetization. Can we see this in these two-dimensional Floquet topological phases? Of course, there's a problem, especially if we think about closed interacting quantum systems of many particles. And the problem is that these systems generically want to heat up kind of to infinite temperature. In infinite temperature state, I mean a state which is in which all correlations look as if they were computed in a state of infinite temperature. Of course, the state is pure if it's a closed system. And the reason this occurs, one way to think about this is in this driven setting, the energy is actually not conserved. What's conserved is the quasi-energy, which is really only conserved modulo omega. So I could always change the quasi-energy by omega, and everything is fine. So you can imagine, kind of, if you think about particles, you could imagine a scattering process which conserves both momentum and quasi-energy mod omega, and this type of process excuse me, would be not allowed in equilibrium, but it's perfectly fine in this driven setting. And basically, this leads to a randomization of the particles in this Floquet Bloch band. So now we might worry that in the end, instead of probing these things, we'll just end up with a very hot state, which is kind of featureless, and we'll not be able to see any of these topological phenomena. So there's few ways around this kind of infinite temperature fate. One of them is to couple the system to an external heat bath. Another one is to basically look at transients, and there have been several works in both of these directions. Another possibility is to try to use disorder and localization in order to prevent the system from heating up. Okay? And this is the direction I'm going to pursue in this talk. Okay? So I'm now going to describe this anomalous Floquet-Anderson insulator, which is indeed a two-dimensional system, which is at the same time it's kind of fully localized. I'll explain exactly what that means. And it's topological. Thanks, Victor. So the reason why this is possible is the fact that the topology in time-dependent system is slightly different than the topology in a static system. And that basically has to do with the fact that these quasi-energies, as we discuss, are periodic are in a circle, are between 0 and omega, and we're basically also in a circle. Thus, if you think about quasi-momentum and energy, it's kind of in this cylinder for a static system, but it's on a higher dimensional torus for a Floquet system. Okay. Now, here's a situation that kind of is born out of this consideration. If you think about a pure chiral mode, we're all told that this is an unphysical situation. If we look at this pure system, a static system with a pure chiral mode, and we apply an electric field, we'll have that the population of particles in the system is not conserved. This is we usually call the U1 anomaly. And this kind of precludes us from having a chiral system in a purely 1D system. However, we all know that we can find chiral states in the quantum Hall effect, and this is perfectly fine, because in the quantum Hall effect, we can kind of never forget about the bulk states. The bulk states, they must have Chern numbers, say, in this case, plus and minus 1, to have one chiral edge state. And the edge state, the bulk states are also delocalized. So there must be delocalized states in the bulk. Thus, we can transfer basically particles from one edge to the other through the bulk states, and total number of particles is conserved, so everything is fine. However, in the anomaly, in the Floquet band structures, we actually don't need this bulk state to cure the anomaly. Right? So because the quasi-momentum and quasi-energy are both periodic, we could perfectly have a situation where particles kind of continue along this line and reappear back from this corner, which is identified with this corner. And this is exactly the situation for these anomalous Floquet-Anderson insulator. So an anomalous Floquet-Anderson insulator has chiral edge states which coexist with a fully localized bulk, and they basically have this kind of dispersion which traverses the Bloch Floquet zone from one corner to the other on each end. Okay, so let me now explain this a little bit more carefully. You can imagine starting from a system which has no disorder and has 0 Chern numbers in the bulk. This is possible because the Chern numbers just indicate the number of edge states above your band minus the number of edge states below the band. Instead of the Chern number, you should actually be calculating a different invariant, which would tell you basically the topological class that the system is in. But once you take this system and you add this order, before I do that, let me just say how I could basically realize this system. So you could imagine two ways. This scenario is only possible in a time-dependent system, right? Because I'm using here the periodicity of the quasi-energy zone. So we've suggested two ways to go with this. One of them is basically to use a system where really the Hamiltonian is strongly modulated. All the hoppings are strongly modulated. You could even reach a situation where the average Hamiltonian is in fact 0. Or you could start from a system with a weak homogeneous drive and kind of try to fold in the Bloch bands in order to reach the situation where the Chern numbers are 0. I'm going to now discuss this system in a slightly greater length. So I'm going to discuss this time-modulated hopping system. So here is a very simple model that achieves this. We take our period and we chop it into 4 pieces. In the first piece, we turn on these red links. We turn them on with a magnitude such that at this quarter of the period, exactly one particle is basically transferred from the black to the white sides and vice versa. Okay, so I fine-tune, for now, I fine-tune the hopping amplitudes. And I do this for these 4 sub-periods. And you see in each one of these 4 sub-periods, I turn on the corresponding links. Now, if you follow the motion of a particle that starts deep in the bulk, you'd see that it just goes around the plaquette and comes back to its original position. Therefore, the bulk states, really the Floquet operator, the evolution of operator for one period is completely trivial. Okay, it's just the identity matrix, in fact, and this gives us this flat band here. However, if you start the particle on the edge, then you notice that some of these, in some of these sub-periods, you can actually not go anywhere. There's no link connecting to your site. And this actually leads to the fact that the particle would be transported 2 sides to the left or 2 sides to the right, depending on which edge it is in. Okay, so this is a situation here. We have these edge states, one chiral edge state on each side of the system, and a completely flat bulk band. Let me just say that this type of kind of single particle dynamics has been recently realized in these all-optical experiments, basically by modulating the distance between waveguides to emulate these hopping amplitudes. Okay, so now we could add this order to these dynamics and ask what happens. Well, since the Chern numbers are all 0, there's nothing that prohibits the system from fully localizing. And this, you can see this in numerical simulations if you study, say, the mean level spacings. Let me not go into the numerical data here. But basically, upon adding an infinitesimal amount of this order, you immediately enter a phase in which the bulk states are fully localized. And then we need to think about what happens to the edge states. So of course, for arbitrarily weak disorder, these edge states cannot disappear because they're chiral. Okay, I'm looking at one side of the system now. But we need to ask ourselves what happens in the spectral region where we had this dispersing bulk band before, say, over here. Here, let's think about taking a cylinder and inserting a flux. Inserting a flux would basically cause a spectral flow. Each of these momentum states flows on to the next state. However, this spectral flow cannot terminate. Right? It cannot terminate in a localized state because localized bulk states do not respond to a flux. Right? They could be localized in a small region, and therefore they do not respond to a flux in the cylinder. Therefore, the only way to kind of cure the situation is to actually have the edge state appearing inside what used to be this bulk region before and having it traverse from one corner of the Floquet Bloch zone to the other, as we discussed before. Okay, so you could test this in numerics. You could try to look at the propagation in each quasi-energy and see that you have an edge state in each of these quasi-energies whereby the bulk is completely localized. So one more thing before I move on, it's important to understand that this is a different phase from a regular Anderson insulator, from a kind of a standard Anderson insulator. And for example, you could see this as you crank the disorder strength. At some point, you actually reach a transition, a phase transition between a kind of ordinary Anderson insulator and this topological Anderson insulator. And this transition, you have to have a delocalized state appearing all of a sudden in the bulk at some finite disorder strength.
That's not the ideal four-step one, right? There you can
no, it's one with sublattice potentially as well. Yeah. Okay. So, so now let me move on to these quantized two-terminal currents. So, if you look at the chiral band, you could basically ask yourself, what happens if I just take this chiral band and I completely fill it up with fermions? So this would be, say, some spectrum of a Floquet system. Of course, this spectrum, as I said, this spectrum is impossible in a one-dimensional system. That's important. One thing important to understand. You might remember the Taulis pump. The Taulis pump actually has both a right and a left mover, but they're separated in energy. But suppose we just have one of these right movers, and we fill it up completely with fermions. If we do that, we can compute the average velocity of particles in this band. And this comes up to be quantized just because the integral over the E decay is quantized. Okay? So a full chiral band indicates that we have basically a quantized current in the system. So we want to basically completely fill up the edge state. And the question is, how do we do that if we now need to connect our system to leads? Right? The problem that if I try to connect the system to leads, if I try to measure something like a differential conductance, I can have particles going in through the leads and absorbing photons, absorbing quanta of omega, and then going out in the different energy than they entered. So I'm going to end up with a very non-quantized quantity. But what you could imagine is actually taking the bias between the leads and basically taking it to be very, very large. Okay? If you take the bias to be very, very large, what you could imagine is that you start filling up all states that are closer to this lead than to the lead with a negative bias. And thus you'll be filling up all of the edge state, maybe plus some bulk bands as well. So let's see a numerical situation. So here's a numerical simulation of this exact setup. So I'm contacting a lead here and a lead here. This has a positive bias and this has a negative bias. And what I'm showing you here is basically the current. It's not the differential conductance, but it's the current per period, or the charge transported through the system per period. And what you should be looking at is this red line. And you see that as I increase the bias, I basically reach a situation where this current is quantized. If I roll up the system and basically kill the edge states, so I'm trying to transport particles through a bulk, I'll see that I have basically an insulator. This is this dashed red line that is at 0 here. And if the system has no disorder, if it's clean, then I actually have no quantization. So it's important to understand that this phenomena is a phenomena in which disorder is necessary in order to reach the quantization. Without the disorder, there's no quantization of this response function. So again, in the limit of large bias, you could also look at the distribution of particles in the system as you increase the bias, and you'll see that indeed you cover an area that basically completely covers the edge state, and then you'd expect, okay, once we completely fill up the edge state, we're going to transport quantized amount of charge between these two leads. But now, if we look at this picture a little bit more carefully, we need to ask ourselves, where is the current actually being transported? The reason is that, remember, if these are fermions and this region is completely filled, then there is a completely filled region has no chance of transporting anything. It's just completely filled, and there is no current in that region. So then, if you accept this, then you have to kind of realize that the only region which can actually support a current is the interface region between the filled and the empty region. That's where the current should flow, because the empty region, of course, doesn't support any current, as well, and so does the filled region. Okay? So you could actually also see this if you look at this exactly solvable model. You'll see that all currents cancel, so the edge currents actually cancel with these current loops in the bulk, except for current loops which protrude the interface between the filled and the empty regions. Okay, so now this is going to be kind of an important step towards looking at this quantized magnetization. So I've tried to convince you that if I start the system in a field where a system is filled in this, say, inner region here, you should think about now an infinite plane with undergoing this dynamics in which I fill up a certain region, okay, and the rest is just empty. So this is my initial state. I let it evolve for a while. You see that it's localized, then therefore this region doesn't break up. It does have some kind of variance at the edges, but it doesn't break up completely. Particles don't fly off to infinity. And then I've just tried to convince you that there is a current between the filled and the empty region. okay, between the yellow and the blue region. And this current, I try to convince you as well, is going to be quantized. Okay, so let's see what this means. So now I want to try to remember what the definition of magnetization. So I'll define magnetization using Ampere's law. So here's Ampere's law in its continuous form. Here it is in its lattice form. So the current on the link is just the difference between magnetizations on the neighboring plaquettes. And now if I kind of take a cut across the system here and I sum the currents along the red line here, right, I see that in the end, this sum, this telescopic sum, is just going to be the difference between the magnetization inside and outside of the system. And on the other hand, I've just convinced you that it's actually also quantized. There's a quantized current running through here. So that means that the magnetization inside this yellow region, deep in this yellow region here, should be quantized. Okay. So now there's a question, can we directly probe this magnetization, or do we always have to rely on some sort of transport currents? And I'll now show you basically an interferometric way to measure these, this magnetization directly. Once you measure this magnetization, you directly, basically using a bulk probe, measure the topological invariant of the system without having to invoke the edge states. The edge states are really at infinity here. Okay? So to do that, we just have to remember the definition of magnetization in equilibrium. In equilibrium, the magnetization is just the derivative of the energy, or the free energy, with respect to the magnetic field. Okay? So far, there was no magnetic field here. But we can imagine adding a weak static magnetic field in the system and basically looking at the derivative of the total quasi-energy with respect to this magnetic field. Okay, that's perfectly well defined. And the claim is that, which I'm not going to prove, but you could have a look at this paper here, that the derivative of the total quasi-energy with respect to the magnetic field gives you the average magnetization over a period. Okay, so it's very similar to the situation in equilibrium, only we use quasi-energies and average over a period. And then you could imagine basically trying to see an energy shift which is caused by adding a weak magnetic field. Okay? What you have to do is basically think about some kind of Ramsey interferometry where you have two type of atom species, say, and say up and spin down, and you only subject spin up. They both undergo these dynamics, this time-dependent dynamics. But for the spin-up atoms, you also add a weak magnetic field, a very weak magnetic field, and then you look at the phase accumulation for the spin-up atoms. Basically, you look at the spin in the xy plane, and the phase shift would just now be proportional, okay, to basically the change in energy or the derivative of the energy with respect to the total flux, which gives us this quantized magnetization. Okay, so that basically the angle now would be this energy shift times the number of periods. And you could see this very well in numerics. Of course, one thing is that the total magnetization of this region is not completely well defined because its area is not well defined. So there should be a kind of a correction which goes down polynomially as a function of the radius, which takes into account the fact that the boundary is kind of fuzzy. And you can see this correction, but leaving this correction aside, the value for this magnetization is quantized. And this correction goes to 0. So the last thing I want to add to this talk is the issue of interactions. So I've kind of advertised this as a way to see topological phenomena in a closed quantum system which might have interactions, and I want to prevent it from heating up. So we need to ask ourselves, is this phase basically stable to adding interactions or weak enough interactions? So if we just take the same dynamics, this order and this modulated hoppings, for example, can we find a phase where upon adding interactions we'll keep on getting this quantized magnetization, for example, for arbitrary long times? Okay. So this is kind of, you could make an analogy to the regular questions in MBL. One thing I want to note that in this system, there's a nice knob which you could turn, and it's the following. So you could take all of the kinetic part of the Hamiltonian, since it's all time dependent in any case, and you could squeeze it all into a kind of a small interval of the period. Okay, so have all of these modulated hoppings on only at this small interval alpha t here, and then for the rest of the time have just this order and the interaction. So all the hoppings are turned off. Okay, so you have this parameter alpha at your control, and what I'll show you is that as you take alpha to be smaller and smaller, the system becomes more and more localized. Basically because the average Hamiltonian is the disorder becomes more and more dominating. So one thing I want to argue now that indeed there is kind of a many-body localized phase here, and the argument would be the following. You could make a rotating wave transformation which basically takes out all the kinetic part, all the kind of clean hopping part of the Hamiltonian. Since if you remember, the evolution operator for one period was just the identity, this is completely periodic. This unitary is periodic. And now we could look at the Hamiltonian in the rotating frame. In the rotating frame, there is no kinetic part. There's only this disorder in the interaction pieces, which I could decompose into a static part and a time-dependent part. So now we've reached a situation where we basically have a static Hamiltonian with disorder in interactions, and we also have some time-dependent, say, hoppings and time-dependent interactions. And if I believe these people, if the frequency is large enough with respect to the disorder strength and the interaction strength, I will find myself in an MBL phase if there is a corresponding MBL phase without interaction. So the extra driving, if the frequency is large enough, would not stabilize MBL. That means that if there's MBL in 2D, and I'm not casting any opinion on this, but if there's MBL in 2D, there should be an interacting AFAI's phase in two-dimensional as well. Okay. One interesting, so if there is such a phase, can we actually probe it using this magnetization probe? So what we could show is actually if you take the unitary evolution operator, you could basically expand it with what's called this local integral of motion. So you make an expansion using this local integral of motions. And basically, if you look at the first term in this expansion, this term actually carries over from the non-interacting case and is quantized in the case of the AFAI. But then there are all other, a whole slew of other quantized quantities, which in the AFAI, as I gave you in the stock, are all zero. Okay? That means basically that if you take the derivative of the energy with respect to the flux, you indeed recover this magnetization. That means you could observe this magnetization also in the quantized magnetization, also in the interacting system. And if you do some numerics, you can indeed, if you look at the level spacing ratio, you could indeed see that as you as you reduce this parameter alpha, as I promised you before, the disorder, the static disorder piece of them then becomes more and more dominant. And it seems like there is a transition from a level spacing ratio of Poisson to GUE, although we did not do any finite size scaling here, so it's hard to really give any very strong conclusion, but there seems to be an indication that there might be a localized or a very long-lived phase here. You could as well look at the magnetization and indeed check that after running the system for many, many, many periods, you still recover this quantized magnetization, which in this case, there are 6 particles, which that would give us magnetization of 6. One thing I think which is an interesting question, so I've kind of discussed the situation for this interacting phase, which is on an infinite disk with no edges. But if there are edges, you might worry, since this edge state is probably going to thermalize. It's chiral. It cannot be localized. Does it cause any destabilization for the MBL phase in the disk? So can we actually have a coexistence of a thermal state in the one-dimensional edge and an MBL phase within the interior? It's not completely clear.
This was studied already, right?
So we don't think it was completely studied. So we don't have an answer. I don't think we found an.
You don't buy this quasi?
No. Right, so with this, I'd like to thank my collaborators and I'd like to thank you for listening. And I'd like just to summarize. So I've talked about probes of 2D phases, for 2D anomalous phases. I've talked about the quantum currents magnetization. I think there are many open questions. I think this is an open question. Andrew might not share the same opinion, but okay. There's the question of higher order invariants, which I've talked about. It's not clear. I mean, we don't have a model that has them non-zero So it would be interesting to see if there are other phases which have these invariants being non-zero. Are there other analogs? So I've given you two analogs. So there is the differential conductance versus current, the differential magnetization versus quantized magnetization. Are there any other generalization to this? And what's the nature of the topological phase transition in the interacting case? And I want to also advertise Andrew's talk, which is going to talk about fractionalized versions of these phases. Okay, thank you very much.